السلام عليكم ورحمة الله طلاب الفرقة الثانية شعبة اللغة الإنجليزية كلية التجارة جامعة المنوفية. In our course Principles of Statistics, we already started introducing the numerical descriptive measures, and we said for any data we have 4 dimensions to describe the characteristics of this data. We can describe center, variation, position, or the skewness of the data. And the last lecture, indeed, we covered, we introduced an overview for all these dimensions. And then we introduced in particular how to calculate the central tendency measures, mode, mean, median. And we introduced how to calculate the position or location measures, in particular quartiles and percentiles. So today we are introducing the measures to describe the variation. So in our today lecture, mainly we are covering this point, how to calculate, how to describe the variation in the data using a range, variance, standard deviation, and we are not introducing coefficient variation, we are introducing a mean deviation based on the reference that we are using. We don't have a coefficient variation and we have a mean deviation. Anyway, I will return back for the coefficient variation in other lecture to say why we need it. So today we are covering the variation measures, and based on the variation measures, I will discuss how we can use the variation measures and the central tendency measures to find out some information about the distribution of the data or the percent of the data, and introducing some theorems, we name it at the Chebyshev theorem and the empirical rule. So starting now with the how to calculate the variation measures. Very simply, how to calculate a range? Just range the maximum minus the minimum, the largest value minus the smallest value. We name it as the range for the data to describe in general the variation. This is the range used to describe in general the range, the variation, the data. The mean deviation to describe the variation around the center using the absolute value. So how to calculate the mean deviation? It's the sum of the absolute deviations around the average divided by their number will give you the mean deviation. In that case, we can see how we can calculate, but still that measure describing the variation around the center. So now we have a center x bar or mu, whatever. So mu for the population data, x bar for the sample data, and then we have the absolute deviations around that center. The variance, the sum of the x minus mu all squared. So for the mean deviation, we are using the absolute value. For the variance, we are using the square deviation, that the absolute deviation, and that the square deviation around the center. So because we are squaring in values in the variance, then you have a unit of measurements and the variance is squared. Then you have to eliminate the square. How to eliminate the square from the variance? Using the standard deviation, that you are using the square root to eliminate the squaring from a unit of measurements. So now we have almost 4 measures to describe the variation. So we can give example for each one, how to calculate the range, mean deviation, variance, and standard deviation. Okay, so if you have any data, very simply, you can calculate a range, just the maximum minus the minimum. So that in this data, the maximum is 80, and then we have the minimum is 20, then 80 minus 20, that equal 60, that's the value of the range, describing the general variation in your data. So that's the calculated range actually. How I can calculate the mean deviation data? We can see that very simply in the data that you have, in this data that you have, to calculate the mean deviation, we can put that in some steps. Step 1, so that the values. Step 1, calculate the mean. Calculate the mean first, and then sum the values divided by their number will give you the value of the mean mu or x bar. Okay, so it's mu if you have population, and it's x bar if you have a sample. So now we have a x bar equal 50. So the sum of these values divided by their number will give you that x bar equal 50. That first step before calculating the mean deviation. So now for each value, to actually apply the formula for the mean deviation, you need to find the sum of the absolute deviation of the values around the center. So each value will subtract the average and find the absolute value, then adding them up. So then you can add another column saying that x minus x bar, each value minus the value of x bar, which is 50. So now 20 minus 50 equal negative 30, and so on. Then finding the absolute value for this column will be that all the values positive, 30, 10, 0, and so on. Adding them up will be 80. So that's the numerator for the formula for the mean deviation. So a mean deviation now equal sum of x minus x bar, that equal 80, divided by number of values. You have only 5 values, that equal 16. So now the variation around the center equal 16. So mostly the typical value in your data that you have the 5 values equal 50, and the variation around this value mostly around 16. So most of the data, so now we have a mean deviation equal 16. So what is the interpretation of that? That means on average in this data, in these 5 values, on average you have the value 50, and most of the data which will be more or less around the 50 by value 16. So we have most of the data in the range between 50 minus 16, okay, 50 minus 16, that the lower limit for the variation of the data, most of the data in that range, and 50 plus 16. So that is somehow how we are presenting the variation in our data. So we have an average of the center is 50, and then the variation around that by 16. So that mostly find out your data, most of your data in the range 50 minus 16 and 50 plus 16. Okay, so that's very simply how to calculate the mean deviation. Now we can continue how to calculate the variance. So if you have this data, that's another example that you have for the citations. We have some values. Indeed, we have 5 values, and then we need to calculate the variance using a formula. The formula for the variation, sigma x minus mu all squared divided by n. So now in numerator we are squaring the deviation around the center. So first that the values, then we can add one column x minus mu. So now what is the value of mu? Adding the values up, then divided by their number, the sum of the values 140 divided by 5 will give you the value for the average, or mu equal 28. You are saying mu because that's for the population data. If it's sample, then you are using that saying x bar. So now we are explaining how to calculate the variance from the population data. If you have population data, you are saying it's sigma squared. I will differentiate between the variance in the case of the sample and the population data. Okay, so we name it as a population variance in that case, and the notation is sigma squared. Okay, so first calculate the value of mu. So sum of adding up the values divided by their number, then mu equal 28, then x minus mu, each value of x minus x bar, then 38 minus 28 equal 10, 26 minus 28 negative 2, and so on. Find the deviations. That indeed the deviations, then squaring the values to be x minus mu squared, and then adding them up will give you a numerator for the variance. Now the variance sigma squared equal sigma x minus mu all squared. So the sum of that column, that equal 534 divided by n divided by 5, that equal 106.8. Now the question. For this data, we have mu equal 28. So now the unit of measurements for the data. So now the number of traffic citations. Then the unit of measurements now is citations. So mu equal 28 citations. Okay, that's the unit of measurements for our data. What would be the unit of measurements for the variance? Now sigma squared, that equal 106.8. 106.8. So what is the unit of measurements for the variance? So for the mean, the same as the data. The unit of measurements for the mean, the same as the unit of measurements for the data. But for the case of the variance, actually, because we are squaring the values in the calculation, then the unit of measurements now it will be squared. So that does not have real meaning to explain. So what is the meaning that the variance equal 106.8 citations square? Does not have real meaning. So now to have real meaning to explain the meaning of the variance, you have to eliminate the square. How to eliminate the square? Mathematically, we are saying that to eliminate the square, you can use the square root. And this is why we are calculating the standard deviation for the variance. The standard deviation equal the square root for the variance, and that giving you the value that the same unit of the measurements for the data. So now the variance equal 106.8, the standard deviation equal the square root for that value, and whatever that value will have the same unit of measurements for the data, and that in that case actually has a real meaning. So in that it's most it will be 10 point something, okay? So most it will be 10 point something, whatever that using the same approximated to be 10, so that mostly the same unit of measurement. So now we have a mu equal 28 citations, sigma squared equal 106.8 citations squared. Does not have real meaning to explain, but is still presenting variation around the mean. Then to explain the variation around the mean using the same unit of measurements for the data, we can use the L sigma that equal almost approximated to 10. So that means the average number of citations equal 28, and most of the time you have the citations between 28 minus and plus the value of sigma. So now arrange, if now I need to plot that, I need to visualize that, assuming it's symmetric data, assuming that. So that the center of the data is 28, as we said before, and then the citation, and then the variation of the citation around that center, mostly actually it will be 10 minus and 10 plus, 10 minus and 10 plus, that the value of the sigma. So now center the value of mu, and the variation around the center the value of the standard deviation. So most of the data, what is the meaning of most of the data? At the end of this lecture, I will give you exactly how we can find the percent of the data that more or less lie around the mean by one standard deviation of the mean. So if you have a center is mu 28 and variation around the center by 1 sigma, so then we have most of the data in that interval. So that means most of the data between 18 and 38. So for this data that we have, the 5 values, the average of the center is 28, and most of the data in the range between 28 minus 10 and 28 plus 10. And at the end of the lecture, we are explaining that using an empirical rule, and we can say if you have symmetric data, then we can find exactly percent for the variation around the center by 1 or 2 or 3 standard deviations. But anyway, what I need from that slide, I need to know how to calculate the variance, how to calculate the standard deviation, and then how to explain the meaning of the standard deviation as the variation around the center. So one point I need to explain in that slide. So just to clear all that. So now we are using mu and we are using sigma squared. So the same, I need to differentiate between you are calculating the mean or the variance from the population data or from the sample data. So now if I'm doing the same as we had before, so that assuming that the population data, now in one table we are plotting notations just to differentiate and to make it clear for you that the population and that sample. Okay. So if you calculate the mean, from the population, we name it as mu. And if you are calculating the mean from sample data, we name it as x bar. The second point, if you are calculating the variance, from the population, it's sigma squared. And if you are calculating the variance from sample data, we name it as S. And we have very simple difference between sigma squared and S squared. How to calculate sigma squared? Sigma x minus mu all squared divided by n. How to calculate an s squared? I will tell you now. We have very small difference that an s squared equal sigma x minus x bar squared divided by n minus 1. So in the case of the s, we are not dividing by n, you are dividing by n minus 1. I will discuss that in the next slide. So in the next slide, we can discuss that we have small difference between sigma squared and s squared. So in sigma squared divided by n, and s squared divided by n minus 1 for some statistical reasons to have actually unbiased estimator, and that is not our point today to discuss. Okay, so if you have the square root for the variance, we name it as the standard deviation. So for the standard deviation, just the square root for the sigma squared, we name it as sigma, and for s squared, we name it as s. So the standard deviation, just the square root for the variance that you have. Whatever the value of the variance, using the square root will be the standard deviation. So whatever from the sample or the population. So just the notations, it's very important now to differentiate. And notations, it's very important to know that in mu, it means population mean, x bar means sample mean, sigma squared means population variance, and the s squared means sample variance. So now s for sample and sigma for population. Just s, the first actually for the sample, so s from sample. Okay, that to be simplified and to be easy to remember indeed. Okay, now I need to find another example for the case of the sample. The same, whatever the data you have, find x minus mu or x minus x bar squared, and then adding them up, divided by n, it will be variance for the population, divided by n minus 1, it will be sample standard deviation. So now another example for the variance from sample data. Now that difference. So now that slide divided by n, in that slide sigma x minus x bar divided by n minus 1. So be careful about you are calculating the variance from a population or the sample data, assuming you have another 5 values. I'm simplifying indeed the values just to show you how to calculate, but indeed whatever the number of values you have, the same way, whatever the way you actually are calculating, whatever the way which you are using to calculate the variance for 5 values, you can use it for 500 or 5,000 of values that you have and you need to calculate the variance for. So now we have an hourly wage, and then we need to calculate the sample variance in the same way. First, you have to calculate the average. Now, because you have sample data, we name it average as x bar. So now we need to calculate first the x bar. So x bar equal 85, the sum of the values that you have, divided by 5, and that indeed will give you the value of the x bar. So now for that area, that I think mostly it will be 17. Okay, so that equal 17. So now we have x bar. Now we need to add another column for x minus x bar. So each value of the hourly wage that you have minus 17 will give you the deviation around the center, around the mean. And then squaring the values, then in first value, 12 minus 17, negative 5, negative 5 squared 15, and so on for all the values. And at the end, adding them up will give you the sigma x minus x bar squared. All the time, sigma x minus x bar equals 0. But that's one of the main characteristics of the mean, that the sum of the deviation around the mean equals 0. So all the time sigma x minus x bar equal 0, and sigma x minus x bar squared all the time is positive. And now it's 40. So the sample variance sigma x minus x bar squared divided by n minus 1, not divided by n, because you are calculating the variance from the sample data. So that equal 40 divided by 4 equal 10. So now we have the sample variance equal 10. Now still the value of the unit of measurements for the variance, it's squared, and that does not have real meaning. What is the meaning that the variance equal $10 squared? Does not have real meaning. To explain that meaning, you have to calculate the standard deviation. So the standard deviation, you have to calculate S, and that equal the square root for the value 10, and whatever the value that you have, it will be now in dollars, which means in the same unit of measurements for the data that you have. So that's the idea. To describe the variation around the center, we have a mean deviation, you have a variance, but the variance squared unit of measurements, you have to use the square root, and then we name it as the standard deviation. Okay. So before actually introducing the Chebyshev theorem, so now any data that you have, I need to actually introduce that point. Before introducing the Chebyshev theorem, I need to discuss the point for the variation around the center that we had in the last lecture and we had in the beginning of this lecture. So any data that you have, assuming it's a square, it's symmetric, assuming it's symmetric data, okay, assuming that. So we said that the center of the data, mostly, you'll find it at the center. And then, assuming the value, that the value for mu minus sigma, and that the value mu plus sigma. And assuming you have data and you have the value of mu and value of sigma, and that mu minus sigma and that mu plus sigma. So mu, that's the center of the data. And then you have the variation around that center by 1 sigma. So that's the idea. So now the point. We are using the standard deviation to describe the variation around the center. Sometimes you have the question that. Sometimes you have the question that. Whatever the distribution of the data is symmetric or not, what is the proportion of the data in that range between mu minus sigma and mu plus sigma? Or what is the proportion of the data in that range? Mu minus, adding another color, mu minus 2 sigma and mu plus 3 sigma. Sorry, 2 sigma still. Okay. And we can another range, wider range. We can add a wider range that mu plus 3 sigma and mu minus 3 sigma. Okay, so if you have the center is mu and the variation around the center, the value sigma. Now can be the question, what is the proportion of data between mu minus sigma and mu plus sigma? Or what is the proportion of the data between mu minus 2 sigma and mu plus 2 sigma, mu minus 2 sigma and mu plus 2 sigma, and so on. So now, 2 points to answer that question. We have 2 ways to answer that question. The first way, using a Chebyshev, you actually using a Chebyshev theorem, and the second way using an empirical rule. And we have 2 differences between them actually. First, to answer that question using a Chebyshev theorem. Chebyshev theorem saying that whatever the value, whatever the distribution of the data is symmetric or not, the proportion of the data, between mu minus k sigma and mu plus k sigma, that equal at least, so that the proportion greater than or equal, okay? At least means greater than or equal 1 minus 1 over k squared. That in terms of probability. So then the probability of x between mu minus k sigma, the probability of x greater than mu minus k sigma and less than mu plus k sigma, that greater than or equal 1 minus 1 over k squared. That's the meaning of the Chebyshev theorem. So the Chebyshev theorem saying that for any set of observations, sample or proportion, the sample or population, the proportion of the values that lie within k standard deviations of the mean is at least, that means greater than or equal, at least 1 minus 1 over k squared, with one condition, that k greater than its integer. And we have, sorry, no, k has to be greater than 1, whatever, integer or not. Okay, so that's the condition, that you have k greater than 1, because if you have k less than 1 or equal 1, that will be 0. So that will be 0 and negative. So cannot be negative, the probability cannot be negative. And if you have k equal 1, that proportion equal actually 0. So 1 minus 1 over 1, that equals 0 if you have k equal 1, and it will be negative, and it will be negative if you have k less than 1. So a Chebyshev theorem, it's very general, regardless the distribution of the data is symmetric or not. Then the proportion of the data between mu minus k sigma and mu plus k sigma, that equal 1 minus 1 over k squared. What is the meaning of that? The meaning of that, we don't have information about the distribution, and just we need to find some approximation about the proportion of the values between a mu minus and a plus specific number of the standard deviations, that we say it's k. I can give you another point for that. So assuming you have data that has a mu equal 5 and sigma equal 1, and you need to find the proportion of the data between mu minus 2 sigma and mu plus 2 sigma. So what is the meaning of that? If you have data that has mean mu equal 5 and has a standard deviation equal 1, then what is the proportion of the data between mu minus 2 sigma, so mu minus 2 sigma, that equal 3, and mu plus 2 sigma, so that equal 7. So if you have data that has the mean equal 5 and the standard deviation equal 1, what will be the proportion or the percent of the data between the two values 3 and 7? So the Chebyshev theorem saying that in general, the percent or the proportion of the data in that interval, at least it will be actually 1 minus 1 over k squared. So that means 1 minus 1 over half squared, sorry, k equal 2. So now we have k equal 2, okay? So now 2 squared 4, then 1 minus 1 over 4 equal 0.75, and percent equal 75%. So if you have data, that's the meaning of the Chebyshev theorem and how we can use it. Chebyshev theorem saying that if you need to find the percent of the data between mu that lie within k standard deviations, which means between mu minus or plus k standard deviations, then you can use this theorem that percent equal 1 minus 1 over k squared. So in our case, 75% of the data, it will be between 3 and 7 for the data that has a mean equal 5 and the standard deviation equal 1. So any data that has a mean equal 5 and standard deviation equal 1, then we are expecting that to have at least 75% of the data in the range 3 and 7, which is mu minus 2 sigma and mu plus 2 sigma. That theorem, indeed, it's not accurate. It's based on the approximation, and we can find that we don't have any information about the distribution of the data is symmetric or skewed. Okay, so a Chebyshev theorem, it's a very general theorem to approximate the percent or the proportion of the data that lie within k standard deviations of the mean. So how can be the question? As I give you now, if you have mu and sigma and k, what the percent of the data between mu minus a specific value of k standard deviations and mu plus k standard deviations? That one of the questions, one of the points, how we can use the mean and the variance together to describe the data and to find the specific percent in specific range. To find out the specific percent of the data in the range based on the mean and standard deviation. Second point now, the graph that I have, that graph I have, okay, that the first graph that I explained. Indeed, if you're adding one information about the distribution of the data, if you're adding one information about the distribution of the data, if you know that the distribution of the data is symmetric, that mu minus 3, okay? So if you know that the distribution of the data is symmetric, then using the idea of the normality approximation, we can prove that the percent of the data between mu minus 1 sigma and mu plus 1 sigma, that equals 68%. That equals 68%. Okay, so we can change the color. Okay, so we said that the center, okay, that our center data, and that mu plus 1 sigma and that mu minus sigma. Using the some approximations, we can prove that if you have symmetric data, then mu minus 1 sigma and mu plus 1 sigma, that in percent indeed 68%. If you have symmetric data, then the percent of the data between mu minus sigma and mu plus sigma, that equals 68%. And that we name it as an empirical rule. If you need to make the interval wider to be not 1 sigma to be 2 sigma, then in that case, you have more percent of the data in that range. So the percent of the data between mu minus 2 sigma and mu plus 2 sigma, that it will be 95% approximated, okay? If you need to make the interval wider to include mu minus 3 sigma to mu plus 3 sigma, then the percent, it will be actually higher. Then it will be mostly 99.7% of the data. What is the meaning of that? The empirical rule saying that if you have the symmetric data, then the percent of the data between mu minus 1 sigma and mu plus 2 sigma, in that range, you have 68%. So in that range, we have 68% of the data. If you make the interval wider to be minus 2 sigma and plus 2 sigma, then you have 95% in that range. So you have 95% in that range of the data. And if you are making that wider to have it mu minus 3 sigma and mu plus 3 sigma, then you have most of the data, we can say almost all the data, that 99.7%. That's the idea, how we can use the mean and the standard deviation together to somehow find the percent of data in a specific range around a center, and that the idea how we can use standard deviation and the mean to describe the variation around the center. So we have center is mean, and then mu minus or plus 1 sigma, we have most of the data, and that's what I said in the beginning of the lecture. What is the meaning of the most of the data? 68% if it's 1 sigma, and then 95% if it's 2 sigma, and then 99.7% if you have 3 sigma, and that covering mostly all the data. So we have two differences. We have two differences between Chebyshev theorem and the empirical rule. Mostly a Chebyshev theorem for any data, symmetric or not, but the empirical rule only for the symmetric data. Second, a Chebyshev theorem, the value of k has to be greater than 1, but can be any value. For the empirical rule, only you are representing a data for 3 values for k, 1, 2, and 3. So that I hope that now it's clear for you how we can use the mean and the standard deviation together to describe the variation and to find percent of the data in a specific range around the center. So that's very simple application, saying that we have the bi-weekly amount contributed by the paint employees to the company profit, and then we have the mean and standard deviation, and the question now, at least what percent, now the question, at least what percent of the contribution lie within a 3.5 standard deviation, lie within a plus 3.5 standard deviation and minus a 3.5 standard deviation. That means if you have a mu and you have sigma, what is the percent of the data, at least what percent of the data between k standard deviations, and you have k actually lies within k standard deviation of the mean, and you have k equal 3.5, then that percent using the Chebyshev theorem. We don't have any information about the distribution. Then when you have k greater than 1, then we can use the Chebyshev theorem, that 1 minus the percent, at least 1 minus 1 over k squared. So now the percent is greater than or equal indeed 0.92. So 92% of the data, it will be within mu minus and plus a 3.5 standard deviation. Okay, so that the idea. The empirical rule I covered already, so that the empirical rule idea, you have just that graph. We can say that the value of mu, and that we have mu minus sigma, and that mu plus sigma, and then we have a second one, that mu minus 2 sigma, and that mu plus 2 sigma. We are making the range wider, then we are making the percent higher. So you make the range wider, you are in the same time you make the percent higher, and that in somehow we are covering mostly all the data at the end if you have a 3 sigma, a mu minus 3 sigma and a mu plus 3 sigma. So that's the general idea. So today we covered, today in that lecture we covered the variation measures, the range, mean deviation, variance, standard deviation, and based on that we introduced the meaning of the empirical rule and the Chebyshev theorem, and mainly both they are based on the center, based on the mean and the standard deviation. And as we said, the main point for the empirical rule, you have symmetric data, and only we have 3 values for k. We have 1 standard deviation and 2 standard deviations and 3 standard deviations, and that is clearly given now in that rule, and that very simple application for that in general point. But the main point, the main difference between the Chebyshev and the theorem and the empirical rule, the first one, the Chebyshev theorem for any distribution, the empirical rule for only the symmetric distributions. The second, symmetric data, I mean. Second difference, that Chebyshev for any value of k greater than 1, for the empirical rule only for 3 values for k equal 1, 2, and 3. Okay, so we covered now all these points. Next lecture, inshallah, I will add another point, how to calculate the mean and standard deviation from the frequency tables or the grouped data. And in that case, we add another point about what is the meaning of the outlier and how we can use or can differentiate between the mean and median in some applications. But till now, today we covered the variation measures and we introduced the empirical rule and the Chebyshev theorem. Thank you very much. And Assalamu alaikum wa rahmatullahi wa barakatuh.